in order to sort of follow this entire notebook, we will be going through a lot of integrations with MLflow, and DagsHub's integration with MLflow is one that is super easy to follow and work with, and that's the one that we'll be using through this tutorial. So if you guys want to follow along, please sign up to DagsHub with the link that is there in the Colab notebook as well, so that you guys can follow along. And I will give you guys say a couple of minutes before we can do that, so that once we're actually going through the notebook, there are no hiccups during no hiccups for you guys. So right, if there are any more questions or any questions at all, at any point during this, please feel free to interrupt me, because that's I'd rather this be more of a conversation than just me talking for 45 minutes straight. And yeah, we'll start in 2 minutes. If there's any questions, please feel free to speak up. So if everyone has everything set up, it we let's get started. So let's start by talking about what we are going to be learning today, right? We'll cover why we need MLflow, what it is, MLflow's general tracking functionality. We'll talk a little bit about runs and experiments, how to log the runs and experiments, and how and where these runs are recorded. Finally, we'll go on, or we'll do a hands-on experience using MLflow, where we basically use our Colab notebook in order to basically use and integrate MLflow with your projects. And hopefully by the end of this workshop, you will be able to explore, use MLflow and integrate it with all of your projects in just a matter of minutes. So that's our overarching agenda. So let's talk about why we need MLflow, right? And if these memes were really an indication of the actual formal truth, they would be proof incarnate. And the reason for that is, in an applied setting, most of machine learning is almost data engineering, and we use well-established techniques with frameworks like transformers or TensorFlow and PyTorch in order to build our architectures. And then it becomes more of an experimentation slash you know yeah, experimentation based paradigm, where you basically want to figure out the best performing hyperparameters or the best performing architecture that fits best to your particular problem and gives you the best performing solution. So the effort and the time that is spent in that entire process is quite underestimated, right? And if you are basically doing this without a or if you're trying to experiment or experiment on your project without doing any notebook logging, it would be, or without logging any of the relevant information as you go along or go about it, it will become very, very hard for you to do that over the extended period of time. And that is simply because humans do not have a fantastic memory, especially when it comes to discussing the interactions between the various changes and hyperparameters that you would probably experimenting with. So one way that you could go about it is using this sort of notebook style setup that my colleague used to use. And it works, it looks pretty neat, right? And it has a lot of good information, and I guess it gives you some sort of indication of how your project is working. So it is definitely better than just using your mental a mental markdown of what everything is or how everything is interacting with each other, right? But if we would actually look at using this in a long-term setting, it does not scale very well. The search functionality in something like Notion is fairly limited, and it also doesn't allow us to easily visualize the information that we have. So while the information for a single experiment may be somewhat easy to track, it is definitely not something that can be done over an entire run, especially if you want to log features that are present within your fitting pipeline, and not just, excuse me, and not just information that is outputted as a result of a training run. So While Notion is a great tool for note keeping, we can't really say the same when it comes to tracking ML experiments and the general workflow. So in comes MLflow, right? We have identified that we have this challenge where we want to log the information that we generate through the series of training runs that we conduct, but we do not really know how we can solve this. And MLflow is basically a one-stop generalizable solution to that. It is an open source tool to manage the entire machine learning lifecycle. It supports the live logging of parameters, metrics, metadata, and artifacts that are generated when running a machine learning experiment. To manage the machine learning models post training, it also has a model registry with a deployment functionality to serve tools using the REST API. So it was created to reduce the complexity in monitoring experiments, ease the reproducibility of results, and cater the need of of a standardized mechanism to register and deploy models to production. So it was introduced in June 2018 by Databricks, and it supports any machine learning library, algorithm, cloud provider. It is completely generalizable and is fully open source. So if you really find something that it does not support and they are not willing to merge it themselves, you can develop it yourself very easily as well. So that is another fantastic functionality or feature that MLflow has. And you can see all of the organizations that use and contribute to MLflow. And the reason for that is fairly straightforward. These guys, in the beginning, right, when they trained machine learning models of their own, use their developed in-house logging tools in order to basically achieve that. However, these logging tools were generally jerry-rigged and were restricted to a particular framework, platform, or programming language. And as a result of that, it became very hard for practitioners to use the same uh, tool for a different task even within the exact same organization. And you have these, you can see, what is it, 20 organizations that are developing the same, or not 20, is it 20? No, it's 24 organizations developing the exact same tool. It just does not make sense. So MLflow basically stepped up and built that open source solution, and all of these platforms or companies now contribute to it. So it becomes better over time as well due to that open source effect. So MLflow has the following four components that are especially relevant to us. The first one is MLflow tracking, which will be the majority of our discussion today, where we are able to log parameters, metrics, and artifacts when running machine learning code. The second one is MLflow projects, which is a reproducible way of packaging and using data science code. So any code that you develop is placed into this MLflow project functionality that they have. Then we have the MLflow registry, which manages the lifespan of your machine learning models. And what I mean by that is once you develop a machine learning model for any given challenge or any given task, you want to ensure it is safe somewhere. And the MLflow registry is just that. It is a database that consists of all of the machine learning models that you have trained, and it manages the life cycle of the machine learning model. So if you develop a new model later on that iterates on the original one, you are able to tag all of your machine learning models accordingly. So anyone or someone on the DevOps side of things can also use the MLflow registry side of the framework to manage the models and just push them to deployment. So as a data scientist, you would probably hand it off to them at this registry stage where both of you interface. Finally, we have MLflow Models, which is the deployment part of the machine learning lifecycle, wherein MLflow is able to host the models as a REST API, as well as encapsulated in a Docker container so that it can be used in a containerized and scalable fashion, which is also fantastic. Finally, we are that sort of covers the theory aspect of MLflow, right? And that should sort of have a basis or establish a basis for what we will be talking about through the rest of the workshop. From here, we will be talking a lot about the tracking functionality, which is this first aspect that we discussed a little bit earlier. So I will give us, say, a break for about a couple of minutes. And if there are any questions, I would be very, very happy to take them right now. And once everyone is set up, we can proceed to the actual uh, to the run recording part of it, and then we'll get to the hands-on part as well. So, yep. Open to take any questions now. Please unmute yourself and yeah, shoot. Okay, let's get to the tracking functionality part of it, right? And now we'll probably go to a bit of the details regarding how runs and experiments work and how we can structure our logging. So let's understand what runs and experiments are. The experiment unit in MLflow can be handled as a project or an approach, a hypothesis that you're attempting to test, for instance. The term run, it merely refers to a unit of execution within the project. More than one run may be associated to a single experiment. So you can have 5 runs that are associated to one experiment, but every experiment, any single experiment can have multiple runs. However, a single run cannot have multiple experiments. So the experiment is basically can be considered simply the hypothesis that you're testing. So for instance, if you want to perform hyperparameter optimization for your learning rate, that becomes an experiment. And all of the different learning rates that you test, say 10 to the power -3 to 10 to the power -6, are all of the different runs. So you would have 4 different runs with 4 different learning rates, and you can pick from those runs when you compare within the experiment which is the best performing run and use that in your final deployment. So each run is an execution of your code which contains the following information. It records the source of the execution, which means the hash of the commit if you are using Git to track your code, and it also contains the original line of code that was utilized for the run. Artifacts, it also logs artifacts that are the output files recorded during a run. So the machine learning model that is generated as a result of your training routine is an example of an artifact. Parameters are stored in a key value format. They are basically information or hyperparameters that are used as part of the training sequence. The learning rate, the image size, basically if you're training decision trees, the depth of a decision tree becomes the hyperparameter. It is basically that. It is stored in a key value format, which really means you have your key, which is the name of your hyperparameter, and your value, which is what value it contains. So in the case of learning rate, your key would be LR and your value would be 10 to the power of -3 or whatever you're using. Metrics are basically the evaluation outputs that you get, like root mean square error or RSC AUC, that are recorded as part of a run. So if you are if you're trying to minimize the loss, that loss becomes our metric, and that is something that is logged throughout the execution of our run. So how and where are these runs that we've been talking about recorded? These MLflow runs can be stored locally in files, either remotely in a tracking server or in a database that is compatible with SQL Alchemy, which is an open source SQL toolkit and object relational mapper for Python. So it basically MLflow uses SQL Alchemy under the hood, and any database that is compatible with SQL Alchemy can be used as a database for MLflow. So the first scenario, which is a good starter technique or a first starting scenario to get started with the platform itself, is MLflow on localhost, right? MLflow, when you import it, it creates or when you create a run, creates a directory called ML runs in your local system, and that basically contains all of the information that you are attempting to log, such as the parameters and the metrics, along with the artifacts, basically everything that we discussed earlier. it has a couple of limitations on collaboration because experiments or results can't be shared with the team. It is only present locally. If you were to share it with a team, you would probably have to zip it into a tarball or something and send it that way, which is not the most efficient, and also subject to the fact that it is not updated dynamically and you have to basically manually share it every time. But once tracking is completed for these ML runs, you can visualize this very easily using their web interface by typing the MLflow UI command uh, through MLflow's command line interface. So once you install MLflow, you will have their command line interface as well as their Python API, and we will take a look at a bit of both, but primarily we will focus our attention on the Python API. So the UI contains the following key features. It contains experiment-based run listing and comparisons, so you can compare two different runs across multiple experiments, basically, and anything. It will visualize it really, really beautifully in a chart, so you can compare how two runs are performing and then decide which is a better parameter. You can download run results directly. If it's local, probably not super relevant, but it is something that you can do, and it's definitely a lot more important when you are using it with a remote tracking server. You can visualize the run metrics, which I just discussed, and you can also search by parameter or metric value, similar to SQL queries. Scenario 2 is using MLflow on localhost with SQLite. The only difference between this process and the previous one is that instead of logging it directly to your file system, it is logging it to a database. So it is a little bit more efficient in terms of how the files are stored and managed. Plus, database searching is also a lot more optimized simply because we are storing our information in the form of a MLflow run. Our third scenario is MLflow on localhost with a dedicated tracking server. This is also similar to the first scenario, but instead of directly logging your information to your file system or to your database, you proxy it through a server that MLflow hosts. And you can set that up using MLflow server from the command line environment. It will launch the tracking server at the default port of 5000. And during your logging, right, while you are training your model, you would ping the tracking server, and that way logs will be generated and stored through the proxy connection. The fourth scenario is using MLflow with a tracking server backend and an artifact store. So now we're getting into a little bit more a more complicated version of what we've discussed previously. So the tracking server, backend store, and artifact stores may all be located on different hosts in distributed architectures. So you could host this on AWS, for instance. Your S3 bucket could be hosted on AWS. Your remote host could be on GCP, and your Postgres SQL server could be on what is a nice third one, Azure. Okay, anything really, your preference. But that is really useful because you can basically optimize for cost as well, especially in an organizational setting. It scales, you can basically pick what service scales best and use that for the given component. So we see that there are four different distinct blocks over here. We have one local host, which is where our machine learning code will actually run. We have our remote host, which contains the tracking server as well as the SQL Alchemy object. And we send all of our metrics, parameters, and our logs to this tracking server, which logs everything to the SQL server. And our artifacts is logged through the S3 remote host using a Boto3 client. So we have these two different sort of directions that we are logging our content. One is our S3 bucket, and the other is our remote host. So it is significant DevOps work, but it scales really, really well. The fifth scenario is the MLflow tracking server enabled with proxied artifact storage access. And what that really means is it is very, very similar, or what it really means is instead of the local host directly pinging the S3 host, the S3 host is also proxied through the MLflow tracking server. So using the the tracking server, which is basically hosted with the REST API, the local host has only one target to ping, and it pings this remote host with the metrics, logs, or metrics, parameters, any general logs that you want to send text-based information, basically, and the artifacts that are generated as part of the training run. All of this is sent to the remote host. The remote host is the one that does all of the management. It will log all of the runs, metrics, params, tags to your PostgreSQL server and or the PostgreSQL database, and all of your models, the images, and any configs through the S3 bucket in your remote host. So again, this takes a very significant amount of development work, but it scales really, really well. The sixth scenario is the DagsHub integration with MLflow. So going through all of the above scenarios can be a bit of a hassle, even for people that have a DevOps background. So to simplify the entire process of setting up the S3 bucket server as well as the remote host, DagsHub decides to do all of the MLOps heavy lifting for you. With every single repository, MLflow provides a free MLflow. DagsHub provides a free MLflow server. You can log experiments with MLflow. You can view the information that it generates under the Experiments tab, and you can also manage all of your training models from the full-fledged MLflow UI that is baked directly into your DagsHub repository. When you create a repository on DagsHub, a remote MLflow server is automatically created and configured with the project. The repository's tracking server is located at the URL of your repository with a .mlflow extension to the end. So similar to how Git servers or Git remotes are hosted with your with the domain name, in this case DagsHub.com, your username, the name of the repository that you set up, and .git. MLflow does it in a we set it up to work in a sort of similar way, where we just add .mlflow to it instead of .git, and that gives us the gives us MLflow's remote endpoint. So in this session, we will be using DagsHub's integration with MLflow and log experiments to a remote server by running the entire running and hosting this entire process in just 3 steps, or in only three simple integration commands. So that is our background for all of the technicalities for how MLflow works under the hood. And next we will discuss how we can integrate MLflow in a more of a hands-on fashion with actual code. We will be using this amazing project, and I will wait another minute or so for questions. If there are any, I would love for you to unmute and say them now. But yeah, we'll give it a minute and then get started again with our hands-on part of things.
Could you elaborate about how you're managing user access, or maybe not access, but preventing from user to access specific experiments of others and stuff like this?
Absolutely. So we have, similar to how a Git repository is structured, you can have a public repository, right? And in a public repository, all of the experiments are public as well. And the MLflow remote contains the authentication mechanisms as well. So that prevents users from just directly logging random experiments to your repository. And if you have a private repository, the MLflow server is also private, so you don't need to worry about other people viewing the experiments if you do not want them to. Okay, let's see. We have a couple of messages in the chat. Neil has taken care of them, so that's awesome. All right, okay. Any more questions? If not, I'll wait for like the next minute, or it's 12:28 right now, so we'll get started at like 12:30. Just to reiterate, you would probably you would definitely need DagsHub's integration if you would like to follow along in the next section. So if you do want to do that, please sign up. And once you have it set up, we will get started with our actual integration part of things. So, well, I guess I can get started. All right, the hands-on experience gets started now. So to demo MLflow's awesome functionality, I chose to use Eric Levinson's project where he trains a neural network to classify images as either containing Mario or Wario. So to shorten the time it takes to train it, I have created a fork that trims down the pipeline and uses a subset of the original data just to make things quicker for us. So let's set up our project in the Colab runtime. So to get started, first please fork the base repository to your account. So this is our base repository, and I would be following along the tutorial as well. So all I have to do is just fork it, and I can set a repository name. I'm happy with it being the same, so that's where I'll leave it. And once you have completed forking your repository, it should be set up for you. So you would basically see an interface that is similar to this. Instead of my username, you should have your username, and it'll be forked from the original repository. And this is basically your entire setup. If you would like to take a look at the MLflow UI, you can directly hit this button, and that would redirect you to the MLflow user interface, which you would get if you would run MLflow server locally. So this is our repository. And going back to the Colab notebook, I will now install the DagsHub client. So that is our in-house set of tools that makes a couple of things faster and quicker, easier to integrate, basically. So next, please enter the username as well as the email for your DagsHub account. I will do the same very quickly. And once that is done, and once DagsHub is installed, I can run this as well. So that will basically set up our variables. Finally, I'm going to generate an Oauth token for improved account security. So instead of logging in manually, I can just log in directly with the Oauth functionality. All I need to do is just press accept, and authentication is succeeded. So this is our MLflow UI, by the way. It does not contain anything because we have not set up anything, but we will do that very, very quickly. So, right, we have our, at this point in time, you should have all of these variables set up. So your username, your email, the repository name, as well as the token that we will use for authentication. And once that is done, we can get started with actually cloning the project. So we can see this is our file system. I will configure Git with this information. If you'd like to change it, feel free to go ahead. But yeah, next I will clone the actual repository itself. And once that is done, I can refresh my page. I should be able to see the entire repository. Next, let's install the MLflow library itself. MLflow is installed using pip. It has several different flavors and versions that you can choose from. Each of them has a different range of support, but you can basically pick what you need for your use case. For today, we will be discussing the default MLflow version, so that is the one that we will install, right? And very similar to how we install the DagsHub client, all you do is just run pip install, and it should do the needful for you. Awesome. Okay. So at this point, we have our MLflow package set up. And to get started, let's discuss the actual project itself, right? Because that's what we're going to baseline all of the logging experiments that we do today off of. So to get started, let's look at the data pipeline of this repository, right? We can see that there is one real major stage within this repository. We have a data input. takes as input, well, obviously our training data, the configuration file, the training file, and as a result of that, it outputs the models that we generate. To take a look at the data that we are working with really quickly, we have this we are basically using screenshots from a video game, and this video game contains or all of the images within this data set contain one of either Mario or Wario. So over here we can see in this bounding box we have Mario, and in this bounding box we have Wario, and we can basically, our objective with this project is, or with Eric's project, is to basically figure out if an image contains Mario or Wario given a unlabeled input. So that is our data pipeline. We can see through the data pipeline that the train.py file is pretty much pivotal to our entire approach. So let's just try running it and see what we get, right? So I will minimize that window, and once we run our training file, we can see it has detected a couple of images and it is beginning to train the model. While we do that, I actually want to open up our training file, and this one, which will be important for later, so that I don't need to open that window again. But yeah, we can see the various components that are present within our training file. We have a get dataset function, which returns image data generators for training, validation, as well as testing. We have our model function that gives us a model with 3 convolutional layers, a single dense layer, and the final prediction. And our actual training part of the script, where we define these 3 hyperparameters, establish our training, test, and validation sets. We get our model itself, fit the model, and then following that, we obtain test loss, test accuracies, and then save that model to a directory, right? And hopefully this thing ends or completes its training super quickly. But the idea is basically just that, right? It has completed finding the images and getting our data sets. It's now training the 5 epochs that we have set up over here. We have a learning rate of 10 to the power -3 at an image size of 128. And once the training is completed, it will run the evaluation process. And once that is done, it saves it to a models directory. So it is now evaluating our model. We get an accuracy of, all right, so it has completed saving the model. If we refresh this, we can see our model and all of the information that is there within it. But generally, if you look at how our training worked, we got not fantastic accuracy. This is a binary classification task, so 37%. We can do a lot better. If we just infer this or like invert this, it becomes closer to 63%, which is awesome. But in any case, this is our entire training pipeline, right? And our objective today is to ensure that we are able to find some way to log all of the information that we generate through the iteration part of this. So if we were to say update the number of epochs to 4 or 6 epochs, right, to see how well that performs, that would be a sort of hyperparameter that we modify. And upon the modification of the hyperparameter, we need to ensure that it performs well enough for, or like we need to ensure that we have some way to track this hyperparameter. And right now that's not done, right? So if I just run this again, what will happen is it will just run these entire 5 steps and overwrite the data. Our model will also be overwritten, so we really don't have any practical way of comparing it at this stage. So let's get started with the actual MLflow integration part of things. Firstly, we import MLflow to the training.py, which we will use to later log our runs. I will do that very quickly. So import MLflow, nice and easy. And in order to create, so first things first, we have completed importing MLflow, right? That is fantastic. But now we need to set up an experiment, because all of our runs are part of an experiment, right? Every single run has to have an experiment that it is associated with. So the first step towards logging anything would be to create an experiment. And there are 2 ways to do it. There is the CLI way, wherein you can use the MLflow CLI to basically just type MLflow experiments create, and give it a name, or you can use the create experiment API call within Python and provided a string input. And this string input is basically what we are providing to it in with a little bit of data management within this get experiment ID function, wherein we call the get experiment by name we API call, provided the name. If it returns as none, it means that an experiment's name does not exist. So we create an experiment with the name. So we are preventing us just double creating experiments and overwriting information. And we return the experiment ID. If the experiment already exists, we just return the ID of that experiment. So this is our function, and it's basically exactly what is covered over here. If we run this script over here, the get or create MLflow experiment.py script, what we will get is the ID of the experiment that we have created with the name Mario_Wario. So if we open up our notebook and say, let me minimize our source, our models, and we see that there is this additional directory that was created that was not previously present. And this directory contains this number 0 and this huge number over here that is similar to the one, or it is exactly the same. You can verify it for yourself if you like. It is exactly the same the number that we have printed over here, and that is basically the experiment ID. So when we asked it to create the experiment, it has done it for us. If we run the same thing again, it will give us the same number and not create anything additional, because we have only one experiment and we're just getting it directly since that name exists. Next, we have to allocate a run to our experiment, and we can start an MLflow run using this copy and paste this to our train.py with the experiment ID that we obtained from here. And okay, my internet connection is unstable. Well,
it's okay, Jinan. You froze for a sec, but now it's okay.
Okay, where was I frozen?
You can continue from the allocate the run to the experiment.
All right, awesome. So right here, what we're doing is we're allocating a run to our experiment. So we have a lot of different runs that we can assign to a given experiment. So what we're doing over here is using the start run API, setting an ID to the experiment, which will be the one that we have obtained right here, in order to assign the run its experiment. And we can begin that sort of integration process by simply adding it to this line right here. So with MLflow start run and setting the experiment ID, instead of just copying this, what I'm going to do actually is I will import the getter create, the function from getter create, and use it from there. Create MLflow experiment ID. All right, awesome. And now I can just call get experiment ID. And it was Mario Wario, I think. Yeah, all right. Mario Wario, and right there. Next, all I need to do is indent the rest of the script so that it falls within the scope of the with block. And once it is done, we have effectively completed assigning the experiment ID to our given run. Next, we need to figure out how we can actually go about logging the logging information to this run, right? So once we set up the run, what will happen is that it will run successfully and everything will be awesome, but we will not have actually logged any data. And that is because we need to explicitly specify the data that we need to log in this manual logging paradigm that we have set up. So there are a couple of ways to log all different sorts of information, and we basically go about that now. The 4 ones that we will be covering today are parameters, metrics, artifacts, and just general text. So parameters, there are two ways of logging parameters. We can either use the log param function, where we give it a key value pair similar to what we discussed earlier, or we can log multiple parameters at the same time by just providing a dictionary, which is a set of key value parameters. So it's much of the same thing. It just prevents us from calling the same log param function multiple times without any reason to. Metrics is also very, very similar to parameters, where we can use the log metric function, provide it a key value pair, and it will log it for us. If we can also do or log multiple at the same time using log metrics, where we provide a dictionary, a set of key value pairs to it, so that it is a little bit faster and the code is a lot easier to read as well. Next, we have artifacts. So we can log artifacts using a by basically providing it a path to a string, and sorry, all of the information that is present within that folder as an artifact. Finally, we have text. So you can log text using the using MLflow logging as well. So if you want to just generate information or text-based log, you can do that as well. You provide the string that you would like to log and the path that you would like to save it. So the file name of the text log that you want to generate, and that will basically do that for you. So that is the text-based logging, and these are the 4 ones that we will cover. MLflow has a lot of additional logging capabilities. To read more about them, please refer to their tracking documentation. They have it set up very, very nicely and in a very easy and digestible format. So you would have no trouble going through and logging any additional type of information that you would like. So now, in order to actually log this information, a practical use case of the 4 different functions that we discussed before are right here. So we have the log parameter function. Log params logs all of our parameters for a single metric. We have this single metric right here. For multiple ones, we provide a dictionary, and that does much of the same thing. For artifacts, we will log our models artifact, and that contains the models directory. And for log text, we just give it a random text and a file name to save it against. So let's get started with actually integrating this. So we want to log all of these parameters after they are defined. So we can do that right here. So ensure that they are present before or like after we have defined them, because otherwise it will simply give us an error. For metrics, we have our metrics that we generate right here. So we will integrate that over here at this stage, where we can log all of our metrics. So we provided a dictionary input. Since we have this like the image size is basically repeated in 2 places, I'm not logging the single parameter as well. For our practical purposes, we only need the multiple function, at least for this specific project. So I'm going to trim up this a little bit to make it look pretty. And once we are done with this, we'd like to log our artifact as well, or our model artifact. And we can do that as well using this simple command that we will place after we have completed saving our model. So that once that is done, our logging is more or less complete. So we can run this entire training script that we have, and it should do all of the needful for us. We can see that it prints the experiment ID. That's because of this function right here. Once the training for this is completed, we should see this ML runs populated with this hash, right? And this hash is the commit hash for like the git hash for our commit, and it contains artifacts, the model directory itself, the exact same one that is present right here. And besides that, we have our metrics that contain our accuracy and our loss, the parameters, again, all of these 3 bits of information that we logged previously, as well as any tags that MLflow assigns. And this is an internal thing that it assigns per run, but we can see that that's basically everything that we have in this structure, all the way on this end. So we have a full complete working demonstration of this MLflow logging. And this is an example of the first scenario that we discussed all the way up here. Where is it? Right here, where we're using our localhost for logging and storing everything within this ML runs directory. So now we want to assign the logging to a remote directory as well, right? So that way multiple people can collaborate on a single repository and work together to perform experiments and build evaluations and efficient inferences, right? The way we can do that is also very, very straightforward. Step one is to first have an MLflow tracking server, which DagsHub takes care of for us. Next, we need to set the tracking URI for our server, as well as set up credentials as OS variables so that nobody can log information to the tracking server without the explicit permission to do so. So we set a username and a password, and these are basically DagsHub credentials. You can use either your token or your DagsHub username, and instead of your password, you can use your token as well. Both of them work just fine. So we're going to set up 3 environment variables right here, and that it consists of information we've already inputted before, and a little bit of string hacking that just builds up our MLflow URI for us to use. So once we have set up these 3 environment variables, we can update the get or create MLflow experiment function to set up our tracking URI. So, and we basically just get our environment variable that we defined earlier. I'm just going to copy this. Right. And that is basically complete. It will now set up our experiment on the remote server instead of logging it locally. So now if we run this file, right, we will see that it will not give us the experiment ID that we gotten previously. And that is because we are now using a remote server and not our localhost. So I will give it a second to run, and it should get us our experiment.py file or our experiment ID. It should not be taking this long. Let me try running it this one more time. Did I set something wrong? No, I don't think I did. Oh, sweet. Okay. Okay. All right. Folks, please try again, and hopefully that it works this time. I'm going to clear up all of this. But yeah, it gives us our new experiment, and we can see that the URI is not, or like the ID is not the same as the previous one because of the fact that we have now set up the experiment on the remote server as opposed to our local file system. So in order to actually set up the training, this is still not enough, because all this does is that it gets or creates the experiment from the remote server and not from our file system. And if we want to actually set it up in our file system, or so to actually log experiments to the local host, all we need to do is perform the set tracking URI step that we discussed over here, and it also is present right here. So I will scroll all the way down to our MLflow section, and right before we have set up our MLflow, we set the right before we start the MLflow, I'm going to set the tracking URI to the URI that we defined in our in the environment variable, and I will also import OS up top so that we do not get a module not found error. So that, and once that is completed, we have basically completed our integration. So if we rerun our code, we will now be able to see our logs to the experiments on this page. So previously you could see that we had 0 experiments, but now once our training run is completed, we should be able to access the entire set of all of the variables that are present as part of our logging for this given experiment. So let that load very quickly.
If you want to ask questions, this is the best time to open your mic or write it down in the chat. And we have Jinan here and also Dean and I to answer all of your MLflow related questions. I will just add to, I think it was Near who asked it. Yeah, I don't see him here. About the team-based access. So basically, DagsHub provides team-based access to the MLflow server, and everyone who is a collaborator in the project have access to the MLflow server. But if you're not a collaborator, then you can't access the server. And this means that, say you have an organization on DagsHub and this organization have multiple teams, the team will have access to the project they're assigned to. If they don't have access to the project, they don't have access to the MLflow remote server. And this is the way that we're managing the access or the team-based access to each MLflow server, storage, Git server, and all the other components of your project that are hosted on DagsHub. So if you have any follow-ups on that or any additional questions, we're here to take them.
And speaking of which, we have our glitch finally sorted. And that aside, we have our exact training run that we had previously with the exact same abysmal accuracy. However, this time we have abysmal accuracy that is logged forever. So we will always remember that this run existed, which is awesome. So we can see over here, we have the hyperparameters as well as the metrics, basically everything that we had defined, and it is present within our remote experiment server. However, we can also know the fact that we have accuracies that update over our stretch of epochs, right? And we definitely want to ensure that we are tracking it across that entire region, because otherwise it becomes extremely difficult for us to understand which one performs better throughout the training run. So next, the way we can sort of go about logging all of this information would be either to take, say for instance, or add to our code a callback that does the logging for us at a per epoch level that you would probably configure to run after every single epoch, or a lot more easily, you would use MLflow's AutoLogger, which is the last thing that we will speak about today. So MLflow's AutoLogger is basically the entire logging process that we discussed, streamlined and made a lot more straightforward for all of your default parameters and information that you will very easily miss. So this AutoLog functionality is available for all of these 9 libraries, all of which are very popular and cumulatively cover 99% of use cases. For the remaining 1%, it is a generalized library, so you could really use anything. And you could use MLflow AutoLog, and it will set up the entire logging procedure. So the artifacts, the metrics, all of it would do it for us without us having to explicitly specify anything. So in order to do that, all we need to do is add the MLflow AutoLog functionality above before we begin our training run. So I would inject it right here basically. And since we're using TensorFlow, or like our library of choice for this project is TensorFlow, I am going to use TensorFlow autologging. So MLflow, if I can spell it right, autolog, and just that's basically it, right? And once I just save it and run this, the entire training procedure runs again in the same as last time. And this time, when we actually refresh our experiments page, we should see we have an experiment that is currently in progress. If it doesn't complete training by the time this loads, because it's super fast. But yeah, we can see that this experiment logging is currently underway, and it is an in progress run, and we don't have test set accuracy and test set loss, which makes sense because we have not completed our training yet. But once we have, that should also be populated. But additionally, we can see we have an accuracy parameter that we did not have before. So let's wait for the training to complete, and we should be able to see the entire experiment in its complete glory very quickly. This is loading fine. Right, so if we take a look at this experiment right here, we can see all of the information, like our accuracy, for instance, that is loaded within the experiment, and it should generate a really nice looking graph for us. But once that is completed, since we discussed previously, we're added MLflow logging. So since we discussed previously that we have set up MLflow logging, and MLflow logging goes to, or MLflow logging refers to every single experiment, or refers to the source code of every single experiment with the hash. We basically, it was always recommended to commit and push your Git project in order for the association with the code to be made a lot more straightforward. So we can do that very quickly and easily, and a fork does not appear, I guess, origin. And that is done. Nothing is added to the commit, which makes sense because we committed twice, but we're pushing to main and ignoring runs, which is also perfect because we do not want to save that data. But that said, we can now integrate. That is basically all of what we had to cover today. You should now be able to integrate any MLflow experiment or MLflow tracking to all of your projects in a very short amount of time. So thank you very much for joining us. I am once again really sorry about the bugs, and this is generally not a concern, but I hope you guys all had a good time. If there are any questions, I would love to take it right now.
I asked in the chat, but I'm curious. So I was looking at the documentation, and for logging artifacts, which figures, images, and like arbitrary dictionaries or log beds, I don't see, there's not like a key parameter in that function. So once you've done that, how do you actually sort of search for or surface that artifact? Is it by just the file system name?
Yeah, pretty much, because it's an S3 bucket, right? So the S3 bucket splits everything by the hash for the run itself, and then within that, all of the artifacts is basically just almost a file system copy. So the directory name is where it would contain all of the anything that you specify within a directory path. And if you have your images, you would just have your images within right over here, like within this path right here.
Okay, but they don't have a key associated with them. Like I have to.
Not. No,
Okay.
Just consider it almost like a subset of your file system. Really, that is the best way to approach it.
Okay.
Right. I will quit sharing. And right, if there are any questions, yeah, that was a perfect time. Right. Cool. We can call it a wrap then, I guess. Thank you guys very much for joining us today. Have a wonderful rest of your day, and yeah, we'll see you all next time.
Thank you all for joining. Bye-bye.